Welcome back as we continue expanding our understanding of intermolecular forces, the phases of matter, and the energy involved with those processes. So, on this particular section, we're going to discuss melting, freezing, and sublimation. Melting and freezing, they are opposite process. And in addition to that, we're going to see how we can use calculations for fusion, which is what we use when we're talking about melting or freezing. So let's begin with this problem. Describe the process of melting, freezing, and sublimation. So let's start with that. So melting is when a solid goes to liquid. Freezing would be when a liquid goes to solid. And sublimation is when a solid goes directly to gas. So in this planet, we are used to see, for example, water going from ice to liquid and from liquid to gas. We never see ice going straight into the gas. It does happen because that's one of the things that happens inside the refrigerator that you don't see, even though the temperature is 0 degrees or below. But sublimation of H2O does happen on this planet. It's just hard for us to see. So let's talk more about melting, freezing, and sublimation. So melting is going from solid to liquid. In terms of the particles, what you're going to have is on the ice, the particle are neatly arranged. It follows a pattern. And you can observe that pattern happening everywhere. So on melting, you're going to have the particles like that, neatly arranged, going into a state where they are more disorganized. During the process of actual melting, you're going to have your solid and the liquid in a perfect equilibrium where they are interchanging from to one another. So on the solid, all you have is just one phase. On the actual melting, you have both phases together, the solid and the liquid. And you can see how on the solid, the intermolecular forces are very active and arranged, while on the liquid, you're going to have more separation now. So on the liquid, which to go from a solid to a liquid, you're going to have to warm up the system, which means the molecules are going to be moving faster. Therefore, they're going to start disrupting the intermolecular forces, and it's going to be more fluid. Once you have enough energy for every single molecule on the solid phase to be moving faster, then all of them would be farther away from each other, not as far away as in a gas, but far away from each other, so it becomes fluid, but they still feel intermolecular forces acting on them. And that's what freezing is, going from the solid all the way to the liquid, going through a middle state where you have both of them in a perfect equilibrium. And as you notice, we're looking at this from the point of view of this graph. And what this graph is showing us is that if you're graphing the fact that we're adding heat, as we add heat, we're also tracking the rise on temperature. As we are adding heat, we can see that the temperature begins to increase. That's when the ice is warming up. And then when it starts melting, you don't see any more change in temperature, so the temperature remains at the melting point. when every single molecule has enough energy to get away from other molecules, then it becomes a liquid and the temperature begins going up again. So this is what we call a heating curve, and we call that a heating curve because we are adding heat to it. And you're gonna notice that there's a phase, a part of the graph where the temperature remains constant. So all this is happening at 0 degrees. And we call this part, we call this a plateau, which is a place where the temperature doesn't change and we're still adding heat, but the temperature is not increasing because it's going all into the molecule. So the molecules can move. Nothing is going to the thermometer, so we don't see the thermometer temperature changing. So whenever you're doing a graph like this, when you are warming up matter or cooling matter, if you see a part of the graph where the temperature doesn't change at all, that's because that is where the phase is changing. On this case, it's going from solid to liquid, and that would be the part where both phases are present in a perfect equilibrium, going back and forward. So that's something you can understand from the heating curve. So to give you a little bit more detail, water below 0 degrees, water is going to be a solid. Above 0 degrees, all the way to 100, water is going to be a liquid. And that's what we see here. The solid, that's where the molecules are on the solid phase. The liquid, that's where the molecules are on the liquid phase. So the part where the temperature doesn't change, that's when you have the solid and the liquid in a perfect equilibrium. So that's what we see on the melting. We talked earlier about vaporization. So if we do the same graph with vaporization, and we do a heat added and temperature in degrees Celsius going up, on that case, we're going to start at 0 degrees. That's where the ice melted and all we have is water. Then at 100 degrees, the water will boil. That's a change of state. So that's going to be a horizontal line. And then you start superheating the steam. So anything over 100 degrees, that's going to be gas. This is going to be your liquid. And this is going to be a perfect equilibrium between the liquid and the gas. So what happens if I take ice and I take it all the way to gas? Well, in that case, I will have to do something like this. I will have to say first, well, I'm doing this with water. So the first thing I know is that I'm gonna be adding heat because this is a heating curve. The temperature is gonna go up in degrees Celsius. And since I'm dealing with water, I know that water melts at 0 degrees and boils at 100 degrees. And I will say, let's say, for example, that I'm starting at minus 45 degrees Celsius. So that's water is going to be a solid there. So I'm going to start warming up my solid all the way to the freezing point. At the freezing point, that's where the solid and the liquid is going to be on equilibrium. Then it's going to become all liquid, and it's going to go all the way up until it reaches boiling point. Then the liquid and the solid are going to be on a perfect equilibrium, and then I'm going to continue heating up until whatever temperature. And I can say, well, below 0, I know this is going to be a solid. Between 0 and 100, that's going to be a liquid. And I'm talking water. That's only for water. And then be above 500, above 100, that's going to be the gas section. And the plateaus are going to be my melting and my boiling, going from solid to liquid. So you can say that the solid ends there and the liquids begin there. The liquid begins there, and the gas, the liquid stops there, and the gas begins there, and in between is a perfect equilibrium between the liquid and the gas, and on the first plateau is a perfect equilibrium between the solid and the liquid. So that would be a heating curve going all the way from minus 45 degrees all the way to, let's say, 125. And if we do it backwards, so that will take care of the melting and the vaporization. What about the freezing? If I was doing a heating curve for freezing, the first thing I would have to say, that makes no sense, because you cannot do a heating curve for freezing, because freezing requires decreasing the temperature. So that means on this case, we will start high, let's say 75 degrees. We know that water has to freeze at 0. So we will have our water at 75 degrees, and if temperature will come down all the way to the freezing point. At the freezing point, the water and the solid are going to be in a perfect equilibrium. Freezing happens at 0 degrees, and after it freezes, then it continues going down. And this is not a heating curve anymore. This is a cooling curve where we are taking away heat. So the temperature is going down, which is what we see here. The temperature is going down. So that means all this is liquid. All this is solid, and this is the perfect balance between liquid and solid. So any question at this point? I wish you can ask. What about sublimation?